Alright, so in today's video we're discussing the last form of parallelism to reach the 5D parallelism promised at the beginning or towards the middle of the series. And before tackling it, if you haven't had exposure to Mixture of Experts, then there is a blog post here linked to understand the general Mixture of Experts architecture that have gained traction and visibility by their use in GPT-4 mixtural and DeepSeek models. And the basic idea is that we, instead of having a single feed-forward model per layer, then we have several parallel models and route tokens through one or the other based on a router. So we have our normal multi-head self-attention, and then our router, which chooses, in this case, which of the 4 experts to route our token through in the feed-forward network. And then we have the post-add recurrent connection and our normalization. And in this case, we have 2 words, one being more, and the other one being parameters in the paper where the Mixture of Expert models were presented. And we get a 65% likelihood ratio or whatever measuring metric you're using to route between the networks, and then an 80% for parameters to go through for feed-forward network network 1. The design of Mixture of Expert layers makes it quite easy to implement parallelism across experts, and it's just called expert parallelism. Since the feed-forward layers are fully independent, we simply put each expert's feed-forward layer on a different device, and compared to parallelism techniques such as tensor parallelism, it's much more lightweight. Since we don't need to split the matrix multiplication, we just need to route the hidden states of a token to the right expert. And an example would be having 16 experts in a Mixture of Experts setting where each GPU has 4 experts if we have 4 GPUs. In practice, expert parallelism typically is used in conjunction with other forms of parallelism, for instance, data parallelism. This is because expert parallelism only affects the Mixture of Expert layers, so as to say the feed-forward neural network, and does not shard the input tokens, such as in context parallelism, which shards tokens along the sequence length dimension. The same thing is the case for sequence parallelism, whereas in sequence parallelism, we shard on the sequence length for the normalization and the post or pre-add recurrent connection. This means our GPUs would be doing redundant compute for all of the non-Mixture of Expert blocks if we only used expert parallelism. So expert parallelism on its own is kind of a moat similar to tensor parallelism, where even though you have tensor parallelism on the multi-head self-attention and the feed-forward neural networks, because of the bottleneck of computing the layer norm, for example, across the entire sequence, then we do not get the same efficiencies because we cannot split it along the head length. So all this is to say is expert parallelism needs to be paired with other methods in order to be effective, similar to many other types of parallelism. And in practice, there are a few tricks to make EP work efficiently, and they're closely tied to model design. For instance, in DeepSeek v3, there's a constraint in the router such that each token is sent to at most m nodes, meaning like m different clusters, and in this case, it's 4. And this is in order to keep the tokens on a single node and reduce communication overhead. So in fact, I think this should be m GPUs. I'm not entirely sure, like they definitely have an incorrect typing here where they're mentioning m nodes and then a single node. But in any case, the idea here is that you don't want to split up the token across the entire network because then you'll have internode latency, which is not fast compared to like NVLink, for example. And finally, while expert parallelism has been around for a while, it is just now gaining traction with the Mixture of Expert architecture being more and more used. For example, in the Gemini 2.5 series, which is the latest series from DeepMind/Google, Mixture of Experts is used for all of the models that are available. Okay, now we're going to go at a high level over the 5 types of parallelism that we discussed, starting with data parallelism, which is essentially applying gradient accumulation to multiple GPUs, which is to say we have multiple micro batches that are passing through different GPUs independently. And then we have tensor parallelism, where we split a input along the hidden dimension. So we have, for example, a sequence length of 1024, so 1024 tokens, and we have a head dimension of 256. So if this is the case, and we have 4 attention heads, or in our multi-head attention, then we will split it up into 4 heads of 64 dimension length, and we'll still pass in the sequence lengths of dimension 1024, but instead it will be split up into each head. So 4 heads of 1024 sequence length by 64 instead of 256 of the head dimension. And then we have sequence and context parallelism, where we're instead splitting along the sequence dimension. For sequence parallelism, it's very nice because layer normalization is independent of the sequence. It just acts on a token independently. But context parallelism is dependent, or rather the attention mechanism requires the entire context, or at least the tokens previous, because we're doing masked self-attention or causal attention. So in this case, there needs to be inter-GPU communication such that we can pass the attention scores between GPUs. And then fourth, we have pipeline parallelism, which means that we split the model up into layers, and then the input is passed through a pipeline in essence, where it goes through each device iteratively, and then in the backward pass also just in the reverse order. And then expert parallelism, which we just discussed. And within data parallelism, we have the zero redundancy optimizer, which has 3 stages, with 0, 1 being simply sharding the optimizer states among the GPUs, so that each GPU only has 1 copy of the optimizer state and there's no redundancy. Then we have 0 redundancy optimizer 2, stage 2, where we shard both the optimizer states and the gradients among the GPUs. And finally, 0, 3, where we shard optimizer states, gradients, and parameters among our GPUs. At this stage, one aspect you're probably curious about is how all these parallelism and zero strategies compare to, interact with each other rather. In other words, which ones should we use and efficiently combine together, and which ones should we keep separated? And we're going to first compare pipeline parallelism and zero redundancy optimizer 3 side by side, as they have very close similarities, but some differences as well. And just worth noting is that when we say a layer in the context of especially pipeline parallelism, what we should say is a set of layers as the basis sharding unit of the model. Because of course, if you have 4 GPUs and 4 layers and you use pipeline parallelism, then each GPU will have 1 layer. But this is just a base case. In reality, we might have like a 32 layer model, and each GPU will have 8 layers, but we just refer to this shard of 8 layers as an abstract layer. So hopefully this is understandable. And now if we compare pipeline parallelism with the zero redundancy optimizer 3, both are ways to partition the model weights over several GPUs and perform communication/computation along the model depth axis, which is to say like along the depth of the model. So like if we have 10 layers, we're cutting it up layer-wise. This means in both cases, so both of these strategies, full layer operations are computed on each device because we're cutting up along the layers, but the layers themselves are intact. And this is as opposed to tensor parallelism or expert parallelism, where computations are performed on sub-layer units. So I think what they're saying here is that in expert parallelism, for example, we're splitting out the feed-forward neural network, and then in tensor parallelism, it's both the feed-forward neural network and the attention heads, the multi-head self-attention, which is split up. But given this compare and contrast with pipeline parallelism 0.3 and TP and EP, which honestly doesn't seem that well motivated, let's just talk about the differences between 0.3 and pipeline parallelism. So in 0.3, we only store a fraction of a layer, which is strange because I told you that we have the layers intact, but even though the layers are fractioned, we essentially assemble them in real time on demand whenever we need a specific layer. So when the computation is happening, we have the full layer, but at any given moment, we might not. And then in pipeline parallelism, in contrast, we always have the full layer, so there's no required communication between GPUs to reassemble layers. And here, I think is the most important difference, because in 0.3, we use communication to transfer weights, like literally since you have a fraction of the weights, you need to transfer weights when it's required for a specific GPU, whereas in pipeline parallelism, we transfer the activations between the GPUs, because once we do, for example, if we have 16 layers and 4 GPUs, once we do the first 4 layers on GPU 1, if we have no interleaving, then the GPU 1 will send the activations from the first 4 layers to GPU 2 so that it can calculate layers 5 to, or yeah, 5 to 9, of course. And then for orchestration, it just means that is it agnostic to the model or not, and both of them can be applied to like any type of model. And then when we talk about implementation challenges, first of all, for zero redundancy optimized 3, it's complex to handle the model partitioning and communications because we are fractioning or putting into different tiny shards all of the layers of the model. And then with respect to pipeline parallelism, it's complex to handle efficient pipeline schedules such that there is limited idle time per GPU. And we remember seeing the DeepSeek methods, which are highly complex but reduce the bubble time, if you will, to a very low margin. And then with respect to scaling, for pipeline parallelism, it prefers a large gradient accumulation to hide the idle time. And when they say gradient accumulation, this means the microbatch size. So if you have more and more microbatches, then this will fill up the model more and more. It's like you having more parallel processes happening and giving more tasks to the GPUs. So this is better for reducing idle time. And then with respect to 0.3, it's good to have a large microbatch size as well. And so when we refer to gradient accumulation, we're talking about the number of microbatches. But then when we talk about microbatch size, we're talking about the size of the individual microbatch. And then a sequence length that is also high to hide communications. And this is because if we can scale these, then it kind of amortizes. This is the language they use, I think somewhere here. Yeah, amortizes the communication cost. So 0.3 and PP solve the same challenge, but involve different approaches, and the choice between both depends on whether you want to focus on communication, on the weights, or on the activations. While they can be combined, it's not often done in practice, as doing so requires increasing the global batch size significantly to amortize the communication costs, creating a trade-off between global batch size, model size, network bandwidth, and training efficiency. I can't visualize this like cost trade-off, but just know that it's a very multi-factor situation. And if they are combined, then 0.3 should be configured to keep the weights in memory during the series of pipeline parallelism microbatches to minimize as much as possible unnecessary communication overhead. So this sentence was unclear to me, and that's why I have this section whited out so that I could show you, once it was necessary, what this actually means in English. So what it's saying is that if we have 0.3 in pipeline parallelism, then we hold weights in memory across the entire pipeline parallelism schedule for each microbatch, which is to say that we do not reshard between each microbatch. That way, you only pay for 0.3's weight communication once per optimizer step, not every microbatch, minimizing needless chatter and keeping your pipeline as efficient as possible. This means that instead of sharding on each microbatch, we only shard on a specific pipeline schedule. And this is kind of sensical. Like if you have this much sharding within your pipeline, then you'll definitely have just insane communication costs and it will not be worth it. So we left off here. I hope this makes this sentence more understandable. And now let's talk about a better compromise, which is to say that 0.1 or 0.2, which focuses only on the optimizer states in the case of 0.1 and on both the optimizer states and gradients in the case of 0.2, can be easily combined with pipeline parallelism and are complementary. Combining them does not raise any actually challenges. So for instance, when DeepSeek v3 was trained, pipeline parallelism was used along with 0.1. And before I end the video, I'll just talk about the connection between tensor parallelism and sequence parallelism, since it's the first thing we discussed in terms of combining different parallelism techniques. So they're naturally complementary and can be combined with both pipeline parallelism and 0.3, as it relies on the distributive property of matrix multiplications, which allow weights and activations to be sharded and computed independently before being combined. And I suppose it here refers to tensor parallelism with sequence parallelism. So let's look at what this diagram shows with tensor parallelism and sequence parallelism, where we have our hidden dimension here, and our batch and sequence length have been essentially put onto one dimension, which is to say that instead of having b squares of s by h, we'll instead line up all of the squares of s by h one by one. So think of a cube that's b by s by h. This is the standard three-dimensional interpretation of a batch size, which has a sequence length s and a hidden dimension h. Well, because it facilitates better our tensor parallelism, since it's only along the head dimension, we'll just flatten the batch and sequence length into one dimension such that we have b squares of dimension s by h. So think of this big cube, and then we're just slicing it along the batch dimension such that we have, once again, b times the square of dimension s by h. This is just flattening a cube. Think of if you have like a physical cube, or even better, think of a stack of papers and just putting the papers one next to the other to flatten it into two dimensions. So this is our input. And then in our tensor parallelism domain, we have a column-wise shard for the self-attention within the self-attention, and then followed by a row-wise shard, and it's the same process for our feed-forward network. It's always column-wise followed by row-wise shard, because this allows us to avoid different additional communication primitives. If you want to know why, then watch the video about tensor parallelism and sequence parallelism. And then in between these tensor parallelism domains, we have our sequence parallelism domain, which splits along the sequence length, in this case for our layer norm. So this is what we have in terms of one transformer block with tensor parallelism and sequence parallelism, which are very complementary, since the tensor parallelism domain is strictly within our multi-head self-attention and our feed-forward neural network, and then the sequence parallelism domain is within the layer norm, as well as dropout if dropout is used, but dropout is not really being used in the state-of-the-art models nowadays. And we have these diamonds here, which represent a reduced scatter, which is essentially consolidating the weights and the parameters that are required to be communicated. Like, once again, I can't really explain this at a low level because I have an entire video for that. So this is just a high-level explanation. Now, what did the authors say about tensor parallelism and sequence parallelism? The main reason we don't want to use TP alone is because in practice, tensor parallelism has two limitations we've discussed in previous sections. First, since its communication operations are part of the critical path of computation, I assume this means like within the residual stream, but I'm not entirely sure what is meant by critical path of communication. It's difficult to scale well beyond a certain point at which communication overhead begins to dominate. I assume that they're saying, since it is a strategy which with high scaling also requires increasingly much more communication. I'm not sure off the top of my head which of the parallelism strategies are the best for scaling. I know pipeline parallelism, for example, scales well compared to other methods. But tensor parallelism is better to be intranode being within the node, and then internode being between the nodes. And that's the first reason. Second, unlike zero redundancy optimizer and pipeline parallelism, which are model agnostic, which means that you can like apply it irrespective of what the model is, like is it a convolutional neural network, whatever it may be. Tensor parallelism requires careful handling of activation sharding, sometimes along the hidden dimension in the TP region, and sometimes along the sequence dimension in the sequence parallelism region. I'm not sure why it's saying sometimes, like literally tensor parallelism is along the head dimension and sequence parallelism is along the sequence dimension. So I'm not sure why they're saying, sometimes. Anyways, but this type of specificity to the transformer, of course, this could be probably adapted to other types of models, but it is not agnostic. Like it depends on like the dimensions and how the model is designed. This makes it more cumbersome to implement correctly and requires model-specific knowledge to ensure proper sharding patterns throughout. As a consequence, when combining parallelism strategies, tensor parallelism will typically be kept for high-speed intranode communications, as I mentioned earlier, between the nodes, while zero redundancy optimizer 3 or pipeline parallelism will be used for parallelism groups spanning lower speed internode communications, as their communication patterns require less bandwidth. For pipeline parallelism, since we're simply passing the activations, the intermediate inputs throughout the model, or can be more easily overlapped with computation. So I just mixed that up slightly, so let me just rehash what I said. For pipeline parallelism, it's because we have nice low bandwidth that we can do internode communication. And then for zero redundancy optimizer 3, it's because it can be more easily overlapped with computation. The main consideration when combining this technique is to organize the GPU efficiently in groups for each parallelism dimension to maximize throughput and minimize communication overhead. So in essence, can we get our cake and eat it too, while being mindful of the scaling limitations of tensor parallelism. For instance, the group of GPUs communicating for tensor parallelism should be kept inside nodes, so they're kind of repeating themselves at this point, because this is like reviewing the high level notions. So that's all for this section, and you can see that in the future video we'll just be discussing more combinations of parallel techniques. Thank you for watching.